All right, absolute maximum and absolute minimum. Let me go ahead and write out these definitions. Let f denote a function defined on some interval I. If there is a number u in I for which f of x is less than or equal to f of u for all x in I, then f of u is the absolute maximum. If there is a number v in I for which f of x is greater than or equal to f of v for all x in I, then f of v is the absolute minimum. Okay, so whereas before the local maximum minimums occurred on these little humps, these hills, or these valleys, the absolute maximum is the absolute highest point of a graph on a given interval. So it could be at the top of a hump, or it could just be the end of the graph, or something like that. It's going to be the absolute highest point, and the absolute minimum is the absolute lowest point. Let's do an example. Okay, for each graph of a function y equals f of x, find the absolute maximum and the absolute minimum if it exists. Alright, so for this one, I'm just going to go ahead and circle the absolute maximum minimums. This here is the absolute maximum. And you can tell because it is the highest point on the whole graph. This would be a local minimum, but this point here is the absolute minimum. Hopefully you guys can see that. This is a valley, so it's a local minimum, but the absolute lowest point is way down here. Okay? Over here, this is the absolute max. And this one, it does not hit this point here. Okay? It just keeps going closer and closer and closer to this point, but it's actually undefined. It's discontinuous at this point. So there is no absolute min. Okay? Over here, once again, we have an infinite discontinuity up here, so there is no absolute max. But the absolute min is down here. And here, absolute min. But it just keeps going up and up and up, so there's no absolute max. Here, actually, so sorry. Over here, it actually goes higher than that point, but it just keeps going up and up, so there's no absolute max. And it's undefined here, so there's no absolute min either. Alright. Extreme value theorem. I'll go ahead and write this out. Alright. If f is a continuous function whose domain is a closed interval AB, then f has an absolute maximum and an absolute minimum on AB. So this is saying that if f is continuous, but there's no discontinuities anywhere, on some closed interval, that means, see here, I'm going to scroll back up. It doesn't continue on forever in one direction. It actually ends, like this one ends here and here. And there's no discontinuities anywhere. Then there has to be a maximum and a minimum somewhere on the interval. The only way there isn't one is if there's a discontinuity, like here, or if it's not a closed interval, it's open on one end, like this one, or like this one, or this one over here. Okay? Alright, you guys go ahead and try this one. Example 6. Use a graphing utility to graph this function. Alright, let's pull out the graphing calculator. Alright. Let's see here. Y equals 6x cubed minus 12x plus 5. Alright, and they want it from x equals -2 to 2. Looks like that. Let's change our window from -2 to 2. Let's see what it looks like now. Okay, so approximate where f has a local maximum and where f has a local minimum. Alright, well, I'm going to also extend my y window a little bit. There we go. We can see that f has a maximum here and a minimum here. In order to calculate the maximum and the minimum, I'm going to go to Second, Calculate, and we're going to use minimum and maximum. So let's find the maximum first. Left bound. So I know that the maximum is somewhere right around here. I don't know exactly where. So I'm going to make sure I'm to the left of there for my left bound. And then I'm going to make sure that I'm to the right of there for my right bound. Guess. Maximum. X equals negative 0.816. Where'd my pen go? There it is. Sorry guys. Okay. I'll go ahead and write this. Negative 0.816 or 0.82 and 11.53. This was the local max. Alright, let's find the local min. Whoop. That's not it. There we go. Okay, local min, second, calc, minimum. I know the minimum is somewhere right around here, so I'm going to try to be to the left of that, and then be to the right somewhere. So, 0.816, okay, so 0.82 and negative 1.53. So 0.82 and 1.53. That was the local min. Okay, now, so this was part A. Part B says determine where f is increasing and where it's decreasing. Alright, well, it's increasing from -2 all the way to its maximum, and then from its minimum all the way up to 2, and then in between -2 and 2, it's decreasing. Oops. This is increasing. All right. Example 7. Find the average rate of change of f of x equals 3x squared. Hopefully you guys remember the average rate of change can be found with this equation. Change of y over change in x, or f of b minus f of a over b minus a. So in this case it would be f of 3 minus f of 1 over 3 minus 1. F of 3, let's see, 3 squared is 9. 9 times 3 is 27. F of 1 would be 3. So we've got 24 over 2, which is 12. Do the same for the next one. F of 5 minus f of 1 over, let me scroll down a bit, over 5 minus 1. So 5 squared is 25. 25 times 3 is 75. 1 squared is 1 times 3 is 1. Or sorry, 3. So we've got 72 over 4, which is 18. F of 7 minus f of 1. Scroll down a bit more. Over 7 minus 1. 7 squared is 49. 49 times 3, I don't know. 147. So I've got 147 minus 3 over 6. So 144 over 6, which is, let's see here, 24. Alright. I'll let you guys go ahead and try that one. Last example. Suppose that g of x equals 3x squared minus 2x plus 3. Find the average rate of change of g from negative 2 to 1. Alright, so we just did that. We're going to, not f, we're looking at g. G of 1 minus g of negative 2 over 1 minus negative 2. So g of 1, I've got 3 minus 2 plus 3 minus, let's see here, negative 2 squared is 4. 4 times 3 is 12. 2 times negative 2, that's positive, or negative 2 times negative 2, that's positive 4. There we go. This becomes a plus. We've got 3 here. So we've got 3 minus 2, that's 1, plus 3 is 4. 12 plus 4 is 16. 16 minus 3 is 13. So I've got negative 9 over 3, which is negative 3. Okay. You know what? I just realized I made a little mistake. This is a plus 3 here. My bad. So this would be 19, which makes this a negative 15, which makes this a negative 5. There we go. Actually, here. We write that a little bit neater. So negative 5 is the average rate of change. There we go. Okay. Part B. Find the equation of the secant line containing this and this. Now, if you guys remember from geometry, a secant line intersects a curve twice. I'm just going to draw a sketch over here. You don't actually have to draw this if you don't want to. Where's my cursor? There it is. If I have some curve, a secant line intersects that curve twice. Okay? So what I have going on here, there's some curve going on. I want to find the line, the straight line that intersects these 2 points. So first thing I have to do, I have to figure out what these 2 points are. Actually, I guess I could keep it red. That's fine. So if I plug in negative 2, we already figured out that I get 4. And if I plug in 1, we already figured out, I'm sorry, switch that. If I plug in 1, I get 19. If I plug in negative 2, if I plug in negative 2, I get 19. If I plug in 1, I get 4. There we go. Okay, so we need to figure out the equation of the line containing these 2 points. Once again, the way I got that, negative 2, if I plug in negative 2 into that equation, I get 19, as I figured out over here. If I plug in 1, I get 4, as I figured out over here. So, first thing I need to do, I need to figure out the slope. The slope, I already know, is negative 5. Okay, and I already have my x and y. So y equals mx plus b. My y is 19, my m is negative 5, my x is negative 2. So I've got 19